Hello, this is the virtual presentation of the optimization of dam shape by Arjun Subramanian, Eric Campui, and Yining Wang. There are 57,000 large dams worldwide. Failures of these dams could result in floods, deaths, loss of irrigation, infrastructure, and is a challenge to construct the dams. When constructing a dam, it has to be kept in mind a dam that's affordable but also has the engineering behind it that can prevent overtopping from natural disasters. Also, keeping in mind maintenance issues to prevent failures from foundation and internal erosion. So, when things don't go well for a dam, a situation like the Banqiao Dam happens where upwards of 90,000 people were killed in 1975 when the Banqiao Dam failed on the River Ru in China. A storm from the Typhoon Nina lasting multiple days rained heavily, and the water was able to surpass the dam and overtop, causing the dam to cave, break way, and flooded the nearby area. So our project is to take into account of the Banqiao Dam story and to know that during the storm, the water level peaked at 118 meters. If we were to design a concrete dam, what would be the optimal size and shape to replace the Banqiao Dam and prevent failure? So we made some assumptions in our problem, such as modeling in 2D, also looking at concrete and estimating the strength and compression, and making an assumption that there are no vertical forces, making it easier to just account for the horizontal forces of the water. The modeling method that we're going to use is a series of beams connected in a skeletal structure and pinned at the bottom. The objective for our problem is to minimize the volume of the dam, making the material cost of the dam minimized as well, and minimize the deflection of the dam, so in the end resulting in a affordable but sturdy dam. So our dam shape is modeled by a quadratic equation, a times the quantity x minus 147.5 squared plus c, where the design variables a and c control that left-hand shape of the dam. When a is 0, the function is a constant, and the c provides it as a straight line. So the left-hand side of the dam would be a straight line, causing a rectangular dam. A, when not 0, will cause a curve and change the concavity of a quadratic equation used to model the left-hand side of the dam. Using MATLAB, we can iterate different values of A and C, and using the resultant volumes and deflections, plot that all together in a graph. As you can see on the right, we're zooming in to the points that have lower volumes and lower deflection. That's what we're trying to optimize and minimize. So what do these blue points mean? Looking at the blue points, you can see 3 example points here on this slide. The green and maroon dam shapes are rectangular, and the yellow point is a curved dam, and you can see their performances as well as the shapes and the values used to create them. And the correlation makes sense with the green, as it is thinner, so it would be less volume, however has a higher deflection because it's so thin. And the yellow point fares much better, as we can see on the graph. Now we want a better point than just yellows, because there's points that are dominating the yellow point. So we're moving towards the Pareto frontier in this slide, moving towards the optimal direction, evaluating all the points against each other to see which one has the least amount of volume and least amount of deflection. We have a frontier marked by the red points, with the deciding factor being whether we want a better deflection or a better volume. That concludes this presentation.